Welcome to our System Syzer seminar today based on the Bell & Gossett System Syzer. It's been around for quite a few years, but there's some changes with it and some very interesting changes going on with codes that we'd like to combine with the System Syzer seminar to get you up to date. First thing you probably need to realize is the history of this. A gentleman by the name of Gil Carson, who was an engineer with Bell & Gossett for over 40 years, invented the System Syzer, along with primary, secondary, the triple duty valve, and the circuit setter. And this gentleman was also an ASHRAE fellow. So he was kind of recognized by ASHRAE and by the trade industry as kind of the father of modern hydronics. My name is Chris Edmondson, and it's a pleasure that I knew Gil, and Gil taught me a lot. I traveled with Gil a lot. He was really the real guy. He was sincerely a good educator and a great big brain guy. This System Syzer thing he came up with is a way to help people. And there's hundreds of thousands of System Syzers out there today that Gil invented. His first original System Syzer was a piece of cardboard. This is a picture of the very first one. And he went home and had this great idea and he put all these scales on there by hand to see if it would work. And it worked quite well enough that Bell & Gossett came along and put it into a plastic round wheel that we're all familiar with called a System Syzer wheel. And we're going to play with it a little bit today because this thing has become kind of the industry standard for sizing pipe. This has become the industry standard for sizing pipe. Now, on this original wheel, which you hopefully have some of them you have in your hands today, are basically 5 scales. The first scale on there is the relationship of BTUs and delta T and GPM. So in scale 1, if you know your load or you know the BTUs, you can calculate gallons per minute required. Once you got your gallons per minute, you go to scale 2 and you size your pipe. Now you've got the friction loss. Go to scale 3 and you have your velocity. Go to scale 4 and you get your total pump head loss. Go to scale 5 for plotting system curves and understanding what a CD is on control valves. So you got all these handy little tools available to you on the System Syzer. And we're going to go through each one of those today during our seminar. And this could be the most important seminar you've sat through on hydronics. If you're going to be in this business of design with chill water, hot water, condenser water, you need to understand this because it's just fundamental knowledge. And it applies to everybody's products. They all work the same way. So what's new? Believe it or not, you can now get your little iPhone System Syzer. And I hope you all have one in front of you. I hope everybody on this phone call either has this or will immediately go online. It's a freebie and download this application seminar. Because what's so neat about it, I've got one in front of me right now, is I carry it with me everywhere I go because I always have my phone. But now I've got a quick and easy way to size pipe, check flow rate, check BTUs, and I got PVC pipe in there. Everybody wondered where PVC pipe was. And the manual System Syzer was limited to 12-inch pipe. This goes all the way up now to much bigger pipe. English or metric? How many times have we sat down with a metric system and go back and forth and GPM and cubic meters per second and back? How many times? And now you got it. It will handle glycol. What percentage? It'll handle any fluid that you have the parameters on to input. So now we've got all that built into it, as well as circuit setters. So now you've got a tool that is extremely useful for you. You can just put it in your pocket and take it with you. There's also a version 4 update of a Windows version that is available to you for free. Just go online to the James and Pleasant's website under Bell & Gossett. It'll take you right to the link and you can download it instantly. It's a gift to the industry. And neat thing about it is it's in a Spanish or English language, which has been very useful to us. Again, metric or English, PVC pipe, all kinds of fluids, and it supports the ASHRAE new standard 90.1 2010, which a lot of people that are listening to this may not be aware of, and it's going to be very important to you to have a tool like the System Syzer in order to meet ASHRAE 90.1 2010. Also, we've added a new System Syzer on psychometrics, and it's available as a free download at the same site. There's some ASHRAE codes coming that demand that you actually take the condensate off of a cooling coil and pump it and use it somewhere in your building. The neat thing about this particular System Syzer on psychometrics on the air side, it will calculate the pounds an hour of condensate that you've got to handle. Pretty neat little trick, and I think this is another one that you really want to download and get your hands on. So let's get back to the story. The original Bell & Gossett system sizer, there is a TEH also available. We'll walk you through how to use the system sizer. So if you want to pick it up sometime, it's online as well. You can download it, and you've got everything there to have a real basic course in hydronic design. So where do we start? We got to start with what would be the old scale 1, and it's just basically the temperature relationship between BTUs, delta T, and load. Just that simple. And if you take a look at the old formula, I know everybody probably understands this, but a BTU is defined as the amount of energy required to raise 1 degree of Fahrenheit for 1 pound of water. To raise a pound of water 1 degree Fahrenheit is 1 BTU. Now, if you plug this into the formula, let's just take 60-degree water, for example. Let's assume specific heat is 1, specific gravity is 1, 8.33 pounds per gallon and 60 minutes per hour. I've got my 500. Now I've got my BTUs per hour is equal to 500 times gallons per minute times delta T. And that's good for 60 degrees. Now, obviously, as I change water temperatures, those parameters will change a touch. But the industry end, that's tight enough. But B&G, as usual, will let you calculate it as tight as you like to calculate it. So what is a ton? And I have a lot of fun in the seminars I do with my young kids. You know, we always talking about my chillers, 1,000 tons, 500 tons. It's not the weight of the chiller. I'm not trying to insult you, just have a little fun. It's defined as the amount of energy available in melting a ton of ice in 24 hours. Very easy math. You take a ton of ice, 2,000 pounds, 144 BTUs of fusion per pound, 24 hours, and you melt it, you got yourself 12,000 BTUs per hour. So that's where the word ton came from, and we keep that ton term around because if you think about it, all the engineers and all the contractors talk about their job. I got a 500-ton job, 1,000-ton job, so the word ton is kind of something we use to measure the size of the jobs that we're dealing with. So let's get into the system sizer. I hope everybody online will take the time to get either the handheld manual one in front of them, the little iPhone one in front of them, or the Windows version, so you can go and practice this. If you don't have it with you now, come back later on and get them beside you and walk through the examples so you fully understand them. You cannot find a better education than learning about the system size and what it can do for you and going through these examples. It's one of the best seminars you'll ever get into if you want to learn. Problem 1, we got a little problem. Talking about this temperature and load thing. If we have available boiler water at 180 degrees and return water at 160, then our delta T would be 20 degrees, as shown in the chart. If we have a flow rate of 600 GPM, what is the actual load, heating load in BTUs? Very simple little thing. Our system sizer scale 1 will give us that answer. Let's just take a quick look how we would set it up. If you go to the manual one, all we do is go to scale 1. We've got a 20-degree delta T, and we got 600 GPM. So we set the little black arrow on 600 GPM shown at the bottom of the screen and go up to the delta T on the top of 20, and you'll see the word 6M. M means 6,000 MBH. So that scale up there, as you noticed on the right-hand side, says MBH, which is thousands of BTUs per hour. And the M makes it another 1,000. So in reality, we got, what, 6 million BTUs when we see 6M. And that's the manual system sizer. And you see it gives you the answer of 6 million BTUs or 600 MBH. Now, as you work your way through this, let's take a quick look at the computer version of this. If we take the Windows version of the system sizer and we plug in, we're going to get a slightly different number, because we're going to go ahead and correct it for the mean temperature of the water that we're pumping. We were going in at 160, so coming out at 180. So what you need to do is you go to your menu and you set it up for the water. Now you've got two choices. You can set it up for 60-degree water, which will give you the exact same calculation as before, 6,000 MBH, or we can correct it for the average water temperature that we're actually using. That's one nice thing about computers. We can calculate it as tight as you like to calculate. So when we do that, we go to this scale on the menu and we set it up 160 to 180, notice on the right-hand side it's showing a fluid temperature of 170, which is water, and that's the average temperature. So now she's set up, and we do the calculation, and we wind up with 5,870 MPH load because we corrected it for 170 degree water. Hope everybody understands the manual setup is for 60 degrees, and you can default this one to 60, but if you want to correct it for the temperature, it's easily done. So let's get back to the system size again and look at a second example. Suppose we have a situation with a condensing boiler. Now we've been talking about condensing boilers. We want to control that return water temperature to make sure it stays down below 130 so that we condense. In this case, we want to keep 125 degrees. So if we have a load of 125 degrees, got a return temperature required of 125 and a load of 550,000 BTUs per hour and a 30 degree delta T, what GPM would we get? So you see your little example, we're going to the heating source, return temperature T of 125, coming out at 155, and we got a load of 550. What is the GPM required by the pump to circulate that water? And we're going to correct this for the average temperature, which in this case, between 125 and 155, the average would be 140. So here's my setup on my system sizer, and my second setup, I go in and put my low water temperature at 125, my high water temperature at 155, I put in my load at 550, and I've corrected this for 140 degree water temperature, and you see the GPM. That simple, that accurate, and it really works quite well. So going back again to the manual original system sizer, you see the same setup, the same idea. And again, go to scale 1. MPH is that white scale, so we'll MPH down to the right-hand side in that right scale. We've got 550 MPH, which is between the 500 and the 600, and we line that up with a 30 degree delta T, and we go backwards and we read the GPM, and you see 37 or 38 GPM. So I hope you're recognizing the manual one, you're going to round it off pretty quick to 37 to 38. If you go to the computer one, you've got a much more detailed answer. And if that's for you want to correct everything to the 140 degree water, fine. Just want to make sure you understand the difference in the two. So let's go to another problem. Let's go to system scale, system sizer, problem number 3, still looking at temperature and load. And I repeat, you need to get very comfortable with this. Delta T, GPM, and BTUs. That's what we do every day on chill water and hot water. This is why this system sizer is so important to you. Let's have another example. 3 million BTUs. That's my load. 3,000 MPH. Let's go to chill water. Let's go to a chill water system where we're supplying 42 degree water at a 12 degree delta T. So what would that mean? That would mean that my return would be what? 54. My supply would be 42, and my load is 3 million BTUs. How many GPM do I need in my chill water system through my chiller to deliver that many BTUs? How many? And we're going to correct this for the water temperature. So the difference in 42 and 54, the average I believe would be about 58 degrees, and we're going to correct it for that average. So let's just see what we do. First thing we do, we went and set up the water temperature chart on the right-hand side of the menu. Or if you go to the system size, you can leave it defaulted at 60 degrees and not worry about this. But if you want to correct each one for the average water temperature you're using, each time you make a selection, go set the menu up, go look at the water, and you change the temperature to whatever you're using. In this case, 42 in, 54 out. My average fluid temperature is 48, and I'm going to correct specific gravity, the specific heat, and the viscosity of my fluid based on that water temperature. That's what's so beautiful about this thing. And I think you know where we're going with that. We can always use glycol if you wanted to as well. All right, but let's go back to where we are. So we corrected it to 48 degrees, 42 to 54. I know my load is 3,000 MPH, and you have your GPM there at 500 of 499.84. Round it off to 500. Now, maybe for the first time you've noticed these little padlocks. All right, the little padlocks on the screen are very simple. The one you lock down is the one you want to solve for. In other words, in this case, we want to solve for flow in GPM. So I locked it down. Then I'm putting the other three variables in, temperature out, and load, and it's going to automatically calculate the GPM required at that water temperature to deliver that many BTUs. What a neat little tool, and I'm really, really excited about this. Let's go to example number 4 and really begin to see why your engineers, if you're online, or why contractors really need this tool. What do you do about glycol? Everybody's always asking, what happens when I go to 45% propylene glycol solution to my flow? Well, let's see what happens. You got a tool here to take care of it. Same problem. We got 42 degrees supply, 12 degree delta T, and we got to deliver 3 million BTUs or 3,000 MVH to my load. Does going to glycol change my flow rate? Good question. Let's answer the question. So first thing we do is what? We go to the menu and we change the properties of the fluid we're pumping. That's the first thing we do. And we're no longer going to be pumping water. We're now pumping propylene glycol, which is in the menu already there for you. All you got to do is pick propylene glycol. Then you pick the percentage of the propylene glycol and you put in the temperatures, and now it will correct everything to the new GPM. You go to the menu and change the fluid to glycol, the percentage of the glycol, and you go put your temperatures in, 42 in, 54 out, and look at what happened to your flow rate. It's up to 559 GPM, just a little more than a 10% increase in flow rate required when you go to glycol versus water. So your pump's got to be bigger. You may have to have a bigger piece of pipe. This is important. This is why everybody wants to know, what will glycol do to my system? And you've got a tool here to give them an answer. And I think this is just gorgeous that you got this information and you're able to do this so quick, so accurately, and you can design your jobs accordingly. Let's just keep going now. We've been through the first scale to kind of see what's involved there. Let's go to flow and pressure drop, see what's going on. First of all, I've got the GPM now from scale 1. What size pipe do I need? What is the velocity going on? What is the pressure drop? Well, this is the formula from ASHRAE and from research. This is the equation everybody used for friction. And we've taken that formula and basically just put it into the scale. Also, let's take a look at what ASHRAE says about pressure drops that would be appropriate for sizing pipe. This is a statement from Chapter 22, 2009 ASHRAE Fundamental Handbooks, basically saying to you that a pressure drop between 1 and 4 feet per 100 feet of pipe, make sure you don't miss that, per 100 feet of pipe is reasonable. And maybe a fag of 2.5 feet per 100 feet would kind of be the average they see most designers going to. So now you have a friction loss that ASHRAE is saying is reasonable that you can use to size your pipe by. Now, 90.1 2010 has some additional information, but this is where we're going to start, and we'll cover the rest of it in a few minutes. So how about velocity? Pretty straightforward equation, obviously, but you need to look at velocity because velocity has a lot to do with how you handle the air, and if you get velocities too high, your piping will seem to you will be noisy. So let's take a look. What would be considered high velocities and problems? Here's 100 GPM. And we could have a 1-inch pipe at 37 feet per second. It's in red because not only is that pipe going to be real, real clean, it's going to be real noisy. You're going to erode the pipe. It's ridiculous. You don't really want to do that. 2-inch pipe, as you see, velocity came down. 3-inch pipe we have in blue, and 4-inch pipe in blue because we think those are reasonable velocities for pipe. Reasonable velocities that be quiet, it's okay. What's wrong with a 5-inch pipe? Is the velocity in a 1.6 feet per second? Is anything wrong with that? Yes, it may not be able to move air. And we'll talk about that as we go. There's a minimum velocity required per ASHRAE to be able to move air around your system and get it to your roll air trolls and your air separators and get it under control. You don't want air popping out in places that you don't really want to have around. So what does that mean? Well, here's a publication in 1981. Right out of ASHRAE Transactions by this same engineer named Gil Carson. Did a little research, and there's 2 things you need to keep in mind in hydronics. If you try to take air and move it around in your system, you need to be conscious of the velocity. If you're trying to take air in a roll air troll or an air separator and get air out of the water or a big old buffer tank, you need to be conscious of the velocity of the water to get rid of that air. Basically, a very simple chart that says that if you want to get air separated from the water, slow it down to less than a half a foot per second. If you slow water down velocity-wise to less than a half a foot per second, the entrained air is going to pop out. Now, if it's an air separator, that's a great place to get it, or buffer tank. Now you pop it out where you want to. So you size your buffer tanks, your air separators to slow it down to let the air pop out. Now, suppose you want to go the other way and entrain the air and move it over to the air separator. Then a very simple statement is you need to get it over 2 feet per second. Get it over 2 feet per second. I should actually have a downcomer and have entrained air and bring it down if I keep velocity over 2 feet per second. Pretty neat tricks. Yes, there's a difference in a half a foot per second and 2 feet per second. What happens in there, nobody really understands. Nobody can guarantee the results. This is the two numbers you need to hang on to. You want to move air, keep velocity over 2 feet per second. Now, we mentioned some changes in codes, and this ASHRAE 90.1 2010 thing is coming. It's not enforced everywhere, but it's coming. It will be. So right up front, what are the states already, what version of ASHRAE 90.1 are they on? This is a little website you can go to, and you can check your state. You can check where you are to see what ASHRAE version they're on. The point is, we want to point out to you what's coming. And what's coming is ASHRAE 90.1 2010. Guess what's in there that most people haven't seen yet? Pipe sizing. This is a prescriptive path pipe sizing for condenser water and chilled water. Condenser water and chilled water. They're giving you pipe sizes. Take a quick look, and they're giving you the hours of operation per year and giving you the maximum allowed flow in GPM through the pipe. I have never seen this done before, and most engineers are not even aware. So I'm just trying to make you aware. So going across the top of the chart, you'll see less than 2,000 hours, right-hand side over 4,400 hours, and that changes your pipe size. Plus, other is pretty much constant flow or variable flow. So now you've got another code coming on pipe sizing that you're going to have to meet when you size pipe. You have no choice. You will find this Windows-based version of the system sizer includes this in the pipe sizing. We're going to go through one in a few minutes, but real quick, take a look at this when you go to start looking at flow and pressure drop. You have a right-hand column there that says ASHRAE information. And what you've got to do is plug in how many hours a year that you think you're going to run your pump, which is right out of that table. And you've got to pick whether it's variable flow or other operation, and other operation is pretty much constant flow. Once you've done that, it will not allow you to pick a pipe too small per ASHRAE 90.1 2010. And I think it's extremely important that you understand this. This will make you meeting the ASHRAE codes easier, very easily done. Let's just take a couple of quick examples on the flow and pressure drop piece of this, work our way through it a little bit so you make sure you have a little practice with it. So let's just go to problem number 5. Nothing like having a little problem. Use the same data from problem number 4. The pipe is steel, schedule 40, assuming a total equivalent length of pipe of 2,500 feet. We want to make sure we understand what the cost section is for running this. In other words, what is the operating cost involved? And what is the suitable pipe diameter? What size pipe would you pick? And all this is going to come out of the system size. Remember, the 2,500 feet of pipe would be the equivalent length of pipe. That would be the equivalent feet for the T's, for the elbows, for everything. And that's going to be the friction loss will be based on that. So what pipe size would we use in this particular situation? For 500 GPM, 42 degree in, 12 degree delta T with a load of 3 million BTUs. Well, we go to scale for flow and pressure drop. We plug in our ASHRAE. We said it's going to be more than 4,400 hours of operation per year. We said it's variable flow. All systems basically do have two-way valves now. And we're going to go with steel pipe. And by the way, you could be PVC pipe, copper pipe, or steel pipe. All that's in there. This is what's so fantastic about this. plug in your GPM, which is 500 GPM. It actually is 499.84 from the previous screen because we corrected it for the water temperature. And we plug in 6-inch pipe, and 6-inch pipe turns out to be fine. It meets ASHRAE's recommendations. We're okay. Look over on the right-hand side of the gray screen on ASHRAE 90.1 for 6-inch pipe. The maximum allowable flow rate is 680 GPM. Do you see that? The maximum allowable flow for 6-inch pipe with over 4,400 hours of operation and variable flow is 680 GPM. So all the system size is telling you that 500 is less than 680, 6-inch pipe is fine. And we got a pipe pit. Isn't that amazing? You got your friction loss at 1.68 feet per 100. So you know how many pressure drops are going to be per 100 feet of pipe. We have the velocity, 5.55 feet per second. You want Reynolds number? You got Reynolds number. You want feet per second? You got it. You want metric? Look at the bottom left-hand chart. You got liters per minute, liters per hour, liters per second, cubic feet, and GPM. Wow. Now you got all that information you've been looking for. Look at you got feet per second and meters per 100 meters. In other words, you want to go metric, English to metric. What quicker way are you going to find to do this? This is why you've got to have this. This is just beautiful. You got to have it. Right-hand column, a little bit further down, you can plug in the hours of operation. In this case, we got 10 cents a kilowatt hour. We plugged in 2,500 feet as the total equivalent length of pipe. We'll talk more about that in a few minutes, but just an example. And if you're running 8,000, if you're running the year round, you can change the hours of operation. You have the operating costs. So you've got some way now to estimate the cost of running this system on this particular setup. So I think you see a 6-inch pipe is a good choice. And we went through this in detail, but I think you need to be doing that so you fully understand how this works. Well, let's just go back again and keep looking at some of these velocities and our pipe sizes. Why would ASHRAE be dictating to you the minimum allowable pipe size for this flow rate, whether you're running variable or constant? It's cost, ladies and gentlemen. Look at this chart again. ASHRAE max flow, estimated annual pumping cost. In other words, the smaller the pipe, the more friction loss, the higher the operating cost, the bigger the pump. That's simple. The bigger the pipe, the more the first cost is for the pipe, but the lower the operating cost. So ASHRAE is kind of taking a position in the middle here. So real simple, we picked 6-inch pipe. We said that was reasonable at 5.5 feet per second. Max allowable ASHRAE flow rate 680 GPM. We got an estimated cost of $4,334 per year. Look what happens when I cut the pipe from 5 to 6. I double the operating cost by going from 6-inch pipe to 5. One pipe size reduction, I double the annual pumping cost. I think that's pretty dadgum important. And the system size will show you that if you're trying to calculate. How about length and pressure drop scales? How do we come up with a total pump head we need using the system size? Let's just go a little bit further. Again, look at this chart on the version 4 of the Windows version that you can go online from James M. Pluson's company at our website, download it. It's a free one, no cost. I want you to take a look at this. And every engineer, every designer picking pumps needs this. You need this because it's becoming code. Yes, it's becoming code. Before we go to the code piece, let's take a look at this and get it in your head a little bit. This is a chart. This is a selection chart. You already selected the GPM. You already picked your pipe size. So after you pick your pipe size, which is what we just did, we picked the pipe size, we know the friction loss. Now what? Now we've got to come up with the total pump head required from a pump. So here's how we do this. Next screen. You see I come in here and I fill it. How many elbows do I have? How many T's do I have? How many gate valves? How many butterfly valves? What's the length of my pipe actual runs? Do I have a check valve? Do I have a triple duty valve? Do I have a chiller? In this case, I'm showing a chiller. I have a heat exchanger. Do I have a balancing valve? Do I have a triple duty valve or suction diffusion? All this is built into this table. And you can sit here and plug in each one of those numbers, which you need to be doing, and you'll wind up left-hand side total head loss required for your pump. What a beautiful way to calculate your pump. And what a simple way, because you can have those pressure drops at CVs, in PSI, or feet ahead, and it will automatically convert it back and forth for you so you don't get confused. And how many times do you sit down, you got your chillers and pressure drops and PSI, you got a valve over here in feet, and you got to pull it all together to get your pump head. You're going to have to do this. This is coming. What do I mean by that? A lot of people in this conference call have never seen this statement, and this is out of ASHRAE 90.1 2010 standard that DOE says is going to become energy code in every state in this union. It's coming. Some states are there, some will be there shortly. What does it say new about pump head? Read it, please. It says the pump differential pressure head for the purpose of sizing pumps shall be determined. You can read in detail right quick, but it basically says you have to do a detailed pump head loss calculation with all the fittings, all the devices for the critical circuit, for the critical path. You've got to do that calculation, and you got to put it in the file. Yes, ladies and gentlemen, we have to do a pump head loss calculation in detail and put it in your job file. We've never been told that before. That is new. I think we need to be doing it anyhow, but no more guessing. No more just taking a stab at it. We got to do the head loss calculation, and you have to put it in the file. What better way to do that than with a system sizer? We got everything in it for you already. You can just go through it, make a print screen, and throw it in the file, and you know what you did and why you did it. So what is meant by this critical head loss, this critical circuit? It's a simple little direct return system. And if you had to do the pump head loss calculation on this piping diagram, where is the critical circuit? And I think very simple. You can see that zone number 3, for some unknown reason, has a 100-foot ahead drop at 500 GPM through that zone. And if that's the critical circuit that you've got to do this detailed pump head loss calculation in. In this case, it's just that simple. You have to recognize, as a designer, which loop is the critical loop, and you've got to do the head loss calculations and detail it out and put it in the file. That was basically showing your brake horsepower of 3,000 GPM, 130 foot ahead at 80% efficiency. It's going to be 123 brake horsepower if you pump this direct as shown. Now, real quick, if you would look at primary secondary in this situation, you could do it this way. You put a couple of bridges down at the end. Now the critical circuit, it changes. I've isolated a 100-foot head circuit. Yes, I have more additional pumps, and here's all my pumps at the bottom. But now my actual pumping brake horsepower dropped from 123 to 79 by going to primary secondary. You're beginning to see why ASHRAE wants you to take the time to look at systems and pumping and pump head loss calculations. This is a huge amount of savings just by taking the time to analyze the circuits, do detailed pump head loss calculations, and understand where the head is. This is a must. You're going to be in this business, you're going to have to begin to look at your systems. Detailed pump head loss calculation by ASHRAE, by code, and it's the right thing to do. Running pumps cost money. We want the best designs we can get and the most efficient systems we can get. So you kind of see the difference in the savings there from 123 down to 79. It's pretty huge just by the way we decide to pipe the system. Let's look at the pump head loss calculations on a typical cooling tower. And let's plug this into our system sizer to see how this works, because it really does do a nice job, and I want you to be very comfortable with this. So slow down just a second and get this system in your head. Open system, cooling tower. The design is for 250 GPM with a 4-inch pipe. In other words, we've already gone to the friction loss charts. We plugged in 250 GPM. We met the ASHRAE codes with this, and we come up with a 4-inch pipe. So we start there. So we're coming into this detailed head loss calculation chart, or into that part of the system sizer, already with my pipe size to 4 inches at 250 GPM. Next thing, this is a series counterflow tower. I've got pressure nozzles. And pressure nozzles, in this case, take 7 pounds of pressure on the spray nozzle to make this spray. Crossflow towers, you don't have this number. So the series counterflow towers and crossflow towers are different. In this case, I've got to put the spray nozzle pressure into my pump head. Vertical distance between, this has a lift. This is a cooling tower open system. Cold water deck to the spray nozzles is 8 feet. I've got 4 regular 90-degree elbows, It's a very simple, basic system. Keep it real simple so you can see it. I've got a 4-inch gate valve on the inlet and outlet of the cooling tower. You see the gate valve shown where I can isolate the towers. The pump includes an EE-3 suction diffuser, no startup strainer, and a 4-inch triple D valve. The total circuit piping length is 28 feet of 4-inch pipe. I have a plate heat exchanger there. My plate heat exchanger has a pressure drop of 10 pounds. And my leaving cooling tower water is 85 degrees. Entering at 95, coming back at 85. So what am I pumping? I'm pumping 85 degree water. Now, I want you to do a detailed pump head loss calculation. If you're bored with this, I'm sorry. The code's going to make you do this. That's the message I'm trying to give you. You've got to start doing this. We haven't been taking this much time and picking the pump for the critical circuits. We have to now. By code, you're going to have to do this and put it in your file. It's that critical because of the energy involved in running a pump. And we want to make sure we do the right estimate. So let's take this information. Let's go to our scale. Let's go to our system size. Let's see how it can help us. First thing we're going to do is we're going to correct that water temperature. We said 85 to 95, so we go to the menu where we have fluid property. We could leave it at 60, but let's go ahead and correct it to the average water temperature. 85, 95, average is 90 degrees. So we got water, fluid temperature is 90. We got to correct it to 90 for average temperature. Let's go pick a pipe. Now I said we've already done that. We've already been to the flow pressure drop chart to come up with 4-inch pipe at 250 GPM, and we're using steel pipe. This could be PVC here. That's how flexible the system sizer is. You want to run PVC pipe to your cooling towers? Fine. It's already in here for you. This is steel pipe. You see the pressure drops 3.33 feet per 100 feet of pipe. You see the velocity is 6.3 feet per second. And you see this is based on Schedule 40 steel pipe. And that's what we're using. It's beautiful. We got all that plugged in now. Let's go to our length pressure drop setup. Let's go to that screen of a Windows-based system sizer. How are we going to get our total pump head, which by standard 90.1 2010, by code, we are going to have to do? How are we going to do that? Well, that's just the next chart, and then when you start, the GPM and pipe size flows right in. Remember, we had 3.33 feet per 100 feet of pipe and 4-inch pipe. Remember that? And all that's happened now is it remembers that. It remembers the friction loss is 3.33 feet per 100 feet because we picked 4-inch pipe. Remember, it's been corrected for the fluid we're pumping, which happens to be water at 90 degrees. Could be glycol, could be anything. And now we're getting ready to calculate where that black area is the total pump head loss required. So go to the right and just make sure a couple little tricks for you. You see where it's help with the total equivalent length, help with the TEL box? Click that if you want to do a detailed head loss calculation. If you don't click it, this window will not show up. If you want help in calculating the equivalent pressure drop of an elbow and T's and triple D valves, then you click that little help with the TEL button. This pops up. Remember the pipe run was 28 feet. Remember we had 4 regular 90-degree elbows. Remember we had 2 gate valves. Under the pipe entrance, we're going to say we got a sharp edge. Under pipe entrance, we're going to say we got a sharp exit. You could say yes or no. You could change that. It's not a huge number, but if you have a sudden increase or decrease or a sharp edge, check it. This is going to be detailed. It's going to be a good, accurate head loss calculation. On the left-hand side on the bottom, it says heat exchanger. It says example 1. You can write in there what it is. In other words, you just highlight that, write in heat exchanger, put in 10 pounds, check pounds, and it'll take care of the conversion for you. We said the lift between the cold water deck of the tower to the spray nozzles was 8 feet. So again, type in total static head was 8 feet and check feet. We said we had discharge nozzles or spray nozzles that had a minimum requirement of 7 pounds. Put in 7 and check pounds. You see, you plug in pounds and feet, mixing them up. It will correct it for you. Isn't that beautiful? Coming on the right-hand side, we had a 4-inch triple duty valve. We'll just plug it in. It already knows what the pressure drop is of the Bellinghausen triple duty valve. It also has suction fuses. We just picked the EE-3 suction fuse. We plug it in. And now I think you begin to see we've got everything detailed out and that piping system for a total pump head calculation. We got every nut and bolt listed. Everything in that loop, that critical loop, has been listed. And look over to the left-hand side where the black area is. It has calculated a total pipe length equivalent of 1,576 feet. It's using that 3.33 feet per 100 we got from the previous scale, and you got your pump head. You need 53 feet of pump head to make the system work. Print screen, throw up your file, you met the ASHRAE 90.1 2010 code. Ladies and gentlemen, I'm telling you, you need to get this and practice with it. I cannot think of a better way to spend your time, and you're going to have to do this. This is one of the most useful tools you're ever going to find anywhere. Let's take a little bit more look at some flexibility with this. Let's look at the additional scales on CD and how it works. Suppose you had another problem with the owner calling you and saying, I got 2 chillers here, chiller 1, chiller 2, and it says chiller 1, I don't think I'm getting enough flow through chiller 1. I think I'm short on the flow rate through chiller 1. How can I use the CV chart? How can I use that to maybe help answer the question, am I short of flow? The first thing we want to see if we can determine the actual flow through chiller 1. How can we do that? We know the design flow, the desirable flow rate is 2,200 GPM. So chiller 1, C1 is supposed to be 2,200 GPM. We're going to go to scale 5 on the manual system Syzer. We're going to go to the Windows-based version. We're going to go to the CV chart. And on the little one for the handheld computer, we're going to do the same one. What can we do? If you know the pressure drop and the flow rate of any piece in the hydronic system, then you can take those two numbers and you can wind up knowing what the pressure drop would be at any of the flow rate. It's just kind of that good little square law, as I like to refer to it. So where does that go? What does that mean to us? Let's just see. If the chiller manufacturer said at 2,200 GPM, the pressure drop should be 23 feet, what can we do with that? What do we know? We know that at 2,200 GPM per the chiller manufacturer, the pressure drop is 23 feet. If I know the pressure drop across the chiller at any other flow rate, I can tell you the flow rate. It's magical. It's all balancing math. So let's take a look and see if you can understand this. You got pressure gauges. I got my chiller. Chiller manufacturer says it should be 23 feet of drop at 2,200 GPM through my chiller. All right. What is my actual flow rate on my chiller? That's the question. That's the complaint. What is the actual flow rate, and how are we going to determine that flow rate? We can do it by knowing accurately the pressure drop across the chiller. We know at design it's 23 feet, which by the way is 10 pounds at 2,200 GPM. And now we got gauges on there, and we're seeing an inlet pressure of 43, outlet pressure of 32. We have a gauge pressure drop of 11 pounds. By the way, as an older guy who's been in this business a long time, I'd like you to take those pressure readings with the same gauge. Put 2 gauges on the inlet and outlet, fine. Take your readings, swap them, and take the pressure readings again. They should consistently show you the same pressure drop. What I'm interested in here, ladies and gentlemen, is an accurate pressure drop across the chiller. So I want to make sure you take that reading with the same gauge. If the gauge has a little error in it, if I take it with the same gauge, inlet and outlet, I'm after the drop, I get rid of the error. So in this case, I've done that, and I know that the actual pressure drop is 11 pounds. What is my flow rate? On scale 5 of the manual system Syzer, or if you're using the Windows-based version of the CV scale, what do you know? Well, let's go take a look at what we know. So we go to scale 5, and we look at 11 PSI, and let's see what we got. You're going to find that the actual flow rate is 2,300 GPM. If it's 2,200 GPM at 23 feet, that's 10 pounds. We actually have 11 pounds pressure drop, which I think common sense would tell you that we've got more flow than 2,200 if the pressure drops higher. How do we know that? Here's my scale 5. If you take a quick look at it, it's much easier, this particular one, on the Windows-based version, the computer versions, than the manual chart, but I'm used to the manual chart, so I'm okay with that. See that 2M on scale 5 of the manual chart. Go to scale 5, manual chart, one with a little magical CV on it, and look for the bottom of it, and look for 2M. All right, 2M is 2,000 GPM. The next chart, the next little symbol up is 2200 GPM. You have to interpolate that a little bit. And the pressure drop was 10 pounds, which is on the bottom side. You see PSI 10. Line the 10 up with the 2200 GPM. That's what you know. That's what the chiller manufacturer says is the pressure drop at the design flow of 2200 GPM was 10 pounds. Read up to the top of the manual chart, and that's in feet of head. And you'll see the 23 feet interpolated there. So what you're matching up is 2200 GPM to 23 feet of head on the top chart, or 10 pounds on the bottom, same thing, 10 PSI is 23 feet. You're lining that up because that's what you know. That is the known pressure drop and the known GPM. If I have the known pressure drop and the known GPM, I can give you the flow rate at any other pressure drop. That's the magic of scale 5 of the system size. Now go read 11 pounds. 11 pounds is just one more number up, and you'll see that we are pumping approximately 2300 GPM. And the manual chart takes interpolation, which is a little hard. Us older guys are used to that. You kids are probably used to computers. Go to your computer and run the same system. It's much easier to read. Just go there and put in the known flow and the known head, then put in the unknown pressure drop, which is 11 pounds in this case, and it will give you the unknown GPM, which is probably going to calculate at 2309 GPM, a little bit more than 2300. Is that accurate? So your young kids probably would prefer the Windows-based version or the little iPhone to calculate this, but it's a beautiful tool to have and understand. Let's look a little bit at pump impeller trim and just make sure you understand some of the new codes and how do you trim an impeller, what's involved. So here we go. We've got this system out here. We're going to use the system sizer on. System with a system size. I hope you understand where we're going. Design flow by the engineer is 650 GPM at 76 feet of head. But you know what? Pumps are stupid. They don't know that your design head is 76 feet ahead, and they just might run at some other number. Let's just see what happens in this case. Let's turn the pump on. Here's the pump. Charles, a 1510 4BC pump. The green star is where it's been designed by the engineer. 650 GPM, 76 feet ahead. Where are we? About 83% efficiency, midpoint. Beautiful selection of a pump. Great selection of a pump. Will the system run there? Let's turn the pump on and see what happens. So what size motor should we specify? By the way, I think I'd put a 20 on this to be non-overloading. I think I'd put a 20 horsepower to be non-overloading. So system is now installed and running. Let's check out the pump flow. Let's see what really happened. So I got a pump. I want to read the differential pressure across the suction and discharge tappings on that pump to see where it is on that pump curve. So our pump is generating 63 feet of head. Differential pressure across the pump, when I just turned it on in that system, is 63 feet ahead. I like a pressure gauge that gives me differential pressure. Here's our gauge that's made at actually for water specific gravity of 1 that shows feet of head. And it's got multiple tappings to it, you can see. So I have one tapping to the suction flange, one tapping to the discharge flange of my pump, and I get differential pressure in feet of head. One easy way of getting it if you don't understand the difference in PSI and feet of head. Let's go back to my pump curve. That green star was a design, 650 GPM at 76 feet ahead. Beautiful selection. My pump's not running there. Where is it running? It's running where the red star is. It hasn't been balanced. Nobody's done anything to it. We got too much pump head. Where does it wind up running? Well, it says we have 63 feet of pressure drop across my pump. I have a 9.5-inch pump impeller. I have to be on the pump impeller. So when I go to the left-hand column where my 63 feet ahead is, and run a line straight across to my pump impeller, which is where the red star is, I wind up with 63 feet ahead, and I'm flowing 850 GPM. I am flowing 850 GPM at 63 feet ahead. My design was 650 GPM at 76 feet ahead. System will work, but it's going to use a lot of extra brake horsepower. You may have some zones that are noisy, that the velocity is so high it may be a problem. So how do we balance this? How could a system sizer help us? What can we do? Well, remember that scale 5 on the B&G system Syzer, the manual one, or the CV charts in the Windows-based version where you put in the known and unknown flows and heads. That's where these square charts come in handy. We're going to plot a system curve. We're going to put a system curve on this and see what happens. Reality, we're flowing at the red star. That's the real system curve. The green star is where we thought it would be, but it's not there. So let's take a look. So let's go back and let's try some simple solutions like we normally would do. The first thing a mechanical contractor would probably do here is throttle the triple duty valve back, and we can back the pump up the curve and get back to design flow. In other words, all we're going to do, and I think this picture shows it, we're going to throttle. The little yellow chart shows you, and I'll show you this again. We're running at the red star, and all we're going to do is throttle back on a triple duty valve. We're going to add head. We're going to add friction loss that's not there to force the pump back up the curve so that we're at the design point where the green star is, 650 GPM and 76 feet ahead. That's pretty much the way people like to balance and run off and leave. Does that work? It works. Will the system work? The system will work. What's the problem? We actually saved a little bit of money, didn't we? We went from 17 brake horsepower, 6 cents a kilowatt hour running continuously, $8,000 to $7,400, and all we did was throttle the triple duty valve. And now I'm at 16 brake horsepower. I'm running at design. What's wrong with that? You're wasting a lot of money and you're not meeting the code. That's what's wrong with it. We need to trim the pump impellers or put a variable speed drive and slow this thing down. We know we have too much pump in. Why would we run around wasting energy if we don't have to? So let's use our system Syzer to see how we might go about trimming this pump impeller to reduce the horsepower required and save some additional money. Remember, we're at 16 brake horsepower. That's where we are right now. So what does ASHRAE 9.1 2010 have to say about this one? Take a quick look. Hydraulic systems shall be balanced proportionally, and impellers shall be trimmed or the pump speed adjusted or variable speed drive to meet the conditions. There are some exceptions, 10 horsepower or less, and there's some exceptions about the savings, but in this particular case, we're going to easily have to do it. And I'm going to tell you most jobs need this done. So how are we going to go about this? Well, what do we know? We know the real true operating point is 850 GPM at 63 feet ahead. So we know in the real world the operating point is 850 at 63 feet ahead. Let's do a system curve for that. Let's graph the system curve. So we go to scale 5, the magical CV scale 5 of the manual Syzer, or the CV charts of the Windows-based versions, and we plug in 850 at 63 feet ahead. What do you know? Your known flow, 850. Your known head is 63. And what are we after? We would kind of like to know what head we need at 650. That's design flow, right? We're pumping 850. We kind of like to know what it would be at 650. Now what we're really after is to meet the design need at 650 GPM. So all we got to do once you plug that in, you set that up, and we just go to 650, for example, on this particular screen, and you'll see we need about, what, help me out here, about 36, 37 feet ahead to do 650 GPM. And we pull these particular numbers off, any set of numbers you want to. In this case, we pull them off this way. 650 is 37, 750 is 49. This is this magical square chart right off the system Syzer scale 5. What are we going to do with this? We're going to plot a system curve. And I took each one of those points, little red stars, and I plotted my system curve. That's the real curve. That's where the real world is. That's where we're really operating is 850 GPM and 63 feet ahead. But we're pumping too much water. Wouldn't it be nice to save some money here? So what do we do now? How much flow do you want? The design flow was what? 650. GPM at 76 feet ahead was design flow. All we do is do a little vertical line, and where that vertical blue line crosses the red system curve is our minimum impeller size required to give you 650 GPM, which I think you're going to find is about 37 feet ahead. But notice the brake horsepower. What are you saying, Chris? I'm saying to you that the brake horsepower is dropped. We've gone from a 9.5-inch impeller, not a half-inch impeller, down to what looks like about maybe 7.5 roughly. and the brake horsepower is probably going to be 7.5 to 8 horsepower. So we cut the operating cost significantly. In fact, let's just summarize this. 7.6-inch impeller trim. Look at how much money we have saved by trimming that impeller and or using a variable speed drive and slowing it down. A variable speed drive does the same thing as trimming the pump impeller. You just dial the speed down. I've gone from 17 brake horsepower at initial startup to 7.6 brake horsepower. I've cut the operating cost in half. Now do you see why ASHRAE says you got to do this? And now do you see the power of the system size in helping you do these calculations and making sure things are done right? Based on 24 hours of operating costs at 6 cents a kilowatt hour, you see the savings potential. And now I think you understand why ASHRAE wrote this in the standard and why DOE is saying this is going to become the energy code for every state in the union. How about NPSH calculations? For those of you that have been following James and Pleasant's company, we have a whole hour session online on YouTube on how to do NPSH. So we're going to hit this fairly quick, but I encourage you, if you want to go deeper into NPSH, go online to JMP, research NPSH, and you'll pop up with a more detailed seminar. But basically, the system sizer allows you to calculate the available NPSH. Yes, it does. What are we trying to do here? We've got a little chart to the right-hand side. We want to know what the available net positive suction head is, because if we don't have enough, the top chart on the right-hand side shows the pump working okay. The suction pressure did not drop down below the vapor pressure, so we got no bubbles, we got no cavitation. The bottom chart shows the pressure drop falling down below the vapor pressure, and we're creating gas bubbles and we're cavitating the pump. In other words, there's a pressure drop between the suction flange of a pump and the eye of the pump impeller. And that's what we got on this graph on the right-hand side. We've got the measure of the pressure. That piece of S is the gauge pressure, the suction flange gauge pressure. And it pump flows from the gauge pressure to the eye of the impeller, and because we're changing flow rates and we're putting work to it, the pressure actually drops before it hits the eye of the impeller and starts going back up. And that pressure drop of a pump is the defined required NPSH of a pump. And that pressure drop, if it falls below the existing vapor pressure, will cavitate a pump. So how do we calculate what the available NPSH is so we make sure it's greater than the required? How do we make sure that our available NPSH-A is higher than the NPSH-R? So here we go, my little chart I just talked about. I want to make sure I never let the pressure drop, the required NPSH of my pump, dip down below the available pressure and I cavitate. So the bottom chart shows cavitation, the top chart shows the available greater than the required. And this is pretty much the message of what we're trying to accomplish. Let's go back to the same example I just had. Let's go back. So if I pick the green star, what is the available NPSH at that point? The NPSH required is down at the bottom. So all pump curves have on them the NPSH-R, the required NPSH, the actual pressure drop from the suction flange to the eye of the pump impeller. In this case, at 650 GPM, I'm reading over the right-hand side about maybe 8 or 9 feet required NPSH in feet. You also have meters on it if you want it. So now you've got the required NPSH of my 1510 pump. What is my available NPSH? I have to make sure that my available NPSH-A is higher than the 8 feet required. How are we going to do that? It's a simple little formula. I'm sure you worry about this all the time, but we're going to make it easy for you. It's a simple little formula that basically says absolute pressure, liquid surface level. Let's talk about a coolant tower. So that'd be 0 PSIG. It's got to be an absolute, an open coolant tower. So it'll be 14.7 pounds absolute sea level is the pressure on the surface liquid. What is the elevation of liquid above the pump? So that if a coolant tower is elevated above the pump, then we can add that to our available NPSH. It helps us. What do we lose? What's the H of F? How much is the friction loss? What's the friction drop between my coolant tower and the suction flange of my pump? That's taken away from my available NPSH. So you don't want any strainers, anything in there. You don't want any high pressure drop to take away from the available NPSH. Last piece is, what is the temperature of the liquid I'm pumping? what is the vapor pressure of the liquid I pump? How low can I let the pressure go before it cavitates is the question. Those two numbers will wind up giving you the net available NPSH. Now, we've got a way to calculate it on the system sizer that makes it a lot easier than having to run through this formula. So let's go back to our cooling tower. Remember a cooling tower? Let's just take a quick look at it. Same example we just have. Let's calculate what the available NPSH-A is on this tower. Let's take a crack at it and see if we can do this real quick. We got a pipe size. We've already gone into it. It's 250 GPM, 4-inch pipe. Look at the elevation. We got to know the elevation of the cold water liquid above the suction pump. So in this case, it's 3 feet. The vertical elevation of the cold water, minimum cold water level in our tower above the center line of our pump, and that's 3 feet. There's one 90-degree elbow in the suction pipe. I'm not worried about total pump head here, ladies and gentlemen. I want to know the pressure drop in the suction pipe into the suction flange of my pump. All I'm looking at now is the suction flange of my pump. That's what I'm interested in, just the suction flange. There's only one 90-degree elbow in there. The suction pipe length is 12 feet. Notice I'm not at Myrtle Beach. I'm at 2,000 feet elevation, so my elevation is up, and that's going to reduce the absolute pressure available from the atmosphere. It's going to be lower than 14.7 pounds absolute, and this is going to take care of it. I've got a suction diffuser, EE-3, and I'm going to use leaving cooling tower water at 85 degrees because I'm pumping cooling tower water at 85 degrees. And when you're doing NPSH calculations, that water temperature is critical because that gives you the vapor pressure of the liquid you're pumping. So you got all that information. Let's go see what we do with it. First thing is we go to the menu and we input 85-degree water. We're pumping 85. We need that vapor pressure. This takes care of it. As a matter of fact, if you haven't noticed, look at the bottom there. It gives you the vapor pressure, 0.6 pounds absolute. If we keep the pressure on 85-degree water above 0.6 pounds absolute, it went overboard. If we let the water pressure get below 0.6 pounds, it will. So that's the message of that water temperature. It's so critical, and we're going to calculate that for you. What size pipe? Go to the pipe chart. We already picked a 4-inch pipe for 250 GPM, and we go back to our relationship with the TEL, and we get our head loss calculations. In other words, 4-inch pipe is 3.35 feet per 100, remember? But we're only worried about the pressure drop of the suction pipe. So the TEL pipe run, we're only using 12 feet. Top right-hand side, we'll plug it in 12 feet because that's just the length of the suction pipe, 12 feet. How many elbows do we have in the suction piping? 1. How many gate valves? 1. How many pipe exit? 1. Did we have a triple duty valve? No, there's no triple duty valve on the suction side, but there's a suction diffuser, there's an EE-3, so we plugged it in. So if you kind of got the idea, we're just trying to calculate the pressure drop on the suction piping only. That's all we're trying to do here. And that turns out to be 2.55 feet. Very low number, but remember we're dealing with the available NPSH on a pump, and we've got to know what that number is. So it's 2.55 feet. Next we swing over to NPSH-A system sizer logo, and you see it, we clicked on NPSH-A. We're trying to calculate the available NPSH. And we plug in, first thing we do is we look at, is it an open system? It is. Is the cooling tower above the pump? Yes. So we click the very first one. Open system, inlet above the pump. Then we go to location elevation. Is it at sea level? No, it's 2,000 feet up. All right, so we plug in 2,000 feet. Pipe friction loss came over from the previous chart. It's already there for you, 2.55 feet. It came over from the previous scale. What is the dimension for Z? 3 feet. The higher you raise your cooling tower, the more available NPSH you got. The lower your cooling tower, the less available NPSH you got. In this case, we got 3 feet. Left-hand gray chart shows you the available NPSH is 30 feet, which is very high. We only needed, what, 8 or 9? We got 30, so available NPSH is greater than required. We're fine. What a nice, easy way to accurately calculate NPSH-A. Beautiful way of doing it. Ladies and gentlemen, we appreciate your time. Remember, this Windows-based version of the system size and the little iPhone versions are online and they're free. For you old guys like me, and I'm an old guy with gray hair, I do like that manual system size. The limitation of the manual system Syzer is it's only good through 12-inch pipe. Another limitation has nothing to do with NPSH on it. So I would strongly recommend you guys get the Windows-based versions and you spend some time with this. You cannot find a more important tool for every engineer, every contractor, every young person coming this industry to learn. You need this desperately. Have a great day. If we can be any use to you, send us an email. We'll be happy to talk to you. Thank you for your time.